We are now ready to start talking about section 5.1 in your book. And this is about integrals, sometimes called integration. Now, in the world of calculus, especially when you're first learning calculus, there are really two major parts of calculus: derivatives and integrals. We have spent probably 80 to 90% of this class covering derivatives. That's pretty much all we've done so far. Almost all the class is derivatives. However, all the rest of calculus is about integrals. So right now we're going to do really a pretty brief introduction to integrals, and then if you end up taking another calculus class, you will spend most of your time working on integrals. So what is an integral? Actually, it's sort of like the opposite of the derivative. Or maybe you can say the reverse of the derivative. Or, you undo the derivative. Maybe in the mathematical sense, you could call them inverses. What does that mean? Here's what it means. Let's go back. Take a very basic function. We know all about how to take derivatives, right? 12x squared. What an integral does is, let's start with this. Here's the integration sign. It's this sort of curvy line. And you put inside of it, we say we're going to take the integral of this, and whatever your variable is, you always tack on this dx. This dx sort of tells you what the variable is you're taking the integral with respect to. Now we're going to learn the rules in a minute, but just take my word for it right now. The integral of 12x squared is 12x cubed over 3 plus c, which we're going to talk about this in a minute. But if I simplify this, it's 4x cubed. Now look at this here. Up here, I took the function 4x cubed, and I took the derivative, and it's 12x squared. Here, I took 12x squared and took the integral. I ended up with 4x cubed. It's almost like if I start with the 4x cubed and I take the derivative, I get 12x squared. However, if I start with 12x squared and I take the integral, I end up with 4x cubed. So this is the way they're opposites, like they reverse each other. There's all kinds of different ways to describe it. Now here's what's interesting, especially when you have to do problems where you have to take the integral. You know what you can do? If you're given this problem and you're asked to take the integral, then this is your answer. If you want to check and make sure you've done it correctly, you know what you can do? You can take the derivative of your answer and you better get back what you started with. So anytime you're doing these integration problems, especially on a test where you really want to make sure you didn't make any mistakes, if you're given an integral on a test and you figure out the answer and you want to make sure you did it correctly, if you take that answer and then take the derivative of it, you should get back to what you started with. So you can always check your work. When you're taking integrals, you can always check your work. Now let's take a minute. This is something new. We call this the integration constant. Anytime, and let me say this, these are called indefinite integrals. In a couple sections, we're going to do definite integrals, and the only difference is this problem, a definite integral, you stick two numbers here, one at the bottom, one at the top. This is called a definite integral. And when you do a definite integral, when you're all done, your answer is just going to be a number. You actually have a number. An indefinite integral, there's no numbers here. And most of the time, when you finish, you have some kind of equation with variables, and you always have this integration constant. And even sometimes I forget it. So anytime you take an integral, unless you have these numbers here, you always have to put in the plus c. Now let me sort of do a quick demonstration of why we add this plus c. Let's just start back with two functions that look a lot alike. Pretty simple functions. 2x plus 3, and then 2x squared plus 3, and then 2x squared minus 9. I'm going to take the derivative of both of these. So this first one is going to be 4x, and the second one is also 4x. Sort of interesting how the original functions are not the same, but when I took the derivative, actually derivatives are the same. And I could take a minute and explain why, because remember, derivative is like another, it's like the slope, so it's like these two functions must have the same slope, even though they're sort of different. But no time to go into that now, but that's just interesting. However, let's reverse it. Let's start here, and let's go backwards by taking the integral. So we say we can do that. We can take this number, or actually here, we take the number and we take the integral. So if I take the integral of this, I should get this right here, because they're sort of opposites. They reverse each other. So let's do that. Now once again, in a minute, you're going to learn these rules, but let me just for now tell you that the integral of 4x is 4x squared over 2 plus c. So I have to go and stick in that plus c, which is really, now what's interesting is, you notice both of these, it's 4x here, 4x here. So if I take the integral of this one, I assume I get something like that. And if I take the integral of this one, like this. Now, I'm starting from the same place. So which should it be? Should it be the integral of 4x dx should be 2x squared plus 3? Or should it be integral of 4x dx is 2x squared minus 9? Which one should it be? I mean, you know, the idea is we don't know which one it should be. That's why you put the plus c. C is a constant, because we're saying it could either be 3 or minus 9. If you want us to figure out which one it is, you need to give us more information. So that's why when we take an integral, you always put the plus c, because there's going to be a number there, but unless they give us more information, we don't really know what the number is. And then we'll actually do a couple of problems where we actually have to figure out what this constant is. All right, so let's learn some of the rules of taking integrals. And these aren't too difficult, hopefully. You got to keep them straight, because we've been spending weeks and weeks and weeks on derivatives, and now we're taking integrals. And sometimes you're supposed to take an integral and then you start following one of the derivative rules. So you got to really sort of keep it straight in your head. What am I doing here? Am I taking a derivative or an integral? So here are the integral rules. First of all, what if you have a constant? The integral of a constant. I'll just do an example. 4 dx. No variables, nothing else, just a number. Could be a fraction, could be a decimal, could be negative, just a number. The rule is you simply multiply by the variable. Let's check it, right? I keep saying, if I were to take this and I took the derivative, I should get back to where I started. What's the derivative of 4x plus a constant? With a constant 0, derivative of 4x is just 4. You're back to where you started. So yep, that's true. So derivative of a constant what if you have this? There's really a 1 there. Derivative of 1 times dx is just x plus c. All right, now here's the one that gets used all the time. The power rule. The power rule is when you have a variable raised to a number exponent, right? So the exponent has to be a number. So it's one variable raised to a number exponent. And actually it's a two-step process. That's pretty simple. Write down your variable, then you add 1 to the exponent to get the new exponent. So you take your original exponent and you add 1 to it to get the new exponent. Very straightforward. And there's one more step. Divide by the new exponent. Two-step process. Integral of x to the 5th. Add 1 to the exponent. That's your new exponent, x to the 6th. Then divide by that new exponent. That's it. That's the power rule. So anytime you have a variable raised to a number, once again, just for fun, if we were to check it, what's the derivative of this? It would be 6x to the 5th. X to the 5th. Yep, checks out. So, about derivative of x to the minus 3. Well, this is the power rule. The variable, add 1 to the exponent, you add 1 to minus 3, you get minus 2. Divide by the new exponent. I want to simplify it. Integral of square root of x. Of course, remember our rule in here, you always convert square root to a rational exponent. Square root of x to the 1/2. Add 1 to your exponent. What's 1/2 plus 1? Three halves, right? So x to the 3/2 over your new exponent. Now this is a complex fraction which you'd want to clean up a little bit. And there you go. Actually, for this one, I could have started out the problem and said, what's the derivative of 1 over x cubed? So it's almost like, remember when you were taking derivatives, a lot of times to take the derivative with the power rule, you needed to get your variable raised to an exponent. Same thing with integrals. I don't want to take the integral of this. I want to convert this to where I can use the power rule. So what do? I move this up, and it becomes x to the minus 3. Now let me show you something very interesting that happens when we take integrals. Let's just use our normal rules. Matter of fact, this looks pretty simple, pretty straightforward. What's an integral of 1 over x with respect to x? Well, if we apply the power rule, well, first of all, let's get this in the form where we can use the power rule. So 1 over x is the same thing as x to the minus 1. So now, power rule says you add 1 to the exponent, minus 1 plus 1 is 0, and you divide by the new exponent. And then right away, I'm sort of saying, this is a problem. Why is it a problem? Because in math, we can never divide by 0. So it's like, well, I guess we can't do this. And I will say it's true, you cannot use the power rule. This is like the exception to the power rule, the one exception. Everything else, only -1 as an exponent doesn't work. Every other number as an exponent is going to work. Use the power rule. This is just the one time it doesn't work, because when you got a -1 here, it forces you to put a 0 down here, and you can't have that. So what do? So it turns out this is a special case. So this is like almost like the third rule. And we make this rule for this one special integral. Only this one special integral. Whenever you have 1 over x. Because what it is, it turns out, wow, out of the blue, the natural log shows up again. And as it turns out, it's natural log absolute value of x. So you have to put absolute values here around your x. So this is like a special one-off exception crazy rule, because the power rule doesn't work. Turns out when you take the integral of 1 over x, it's natural log absolute value of x. If the exponent is anything else besides -1, you follow the normal power rule. But this is the one sort of exception. How about, since your natural log setup, how about what do if we're trying to take the integral of an exponential function? So once again, exponential functions, we can do some of them, and the ones we can do are when you have e to a number times x. So really, the rule we're going to learn only works when you have a number times x. So this is not going to be a rule for all exponential functions. It's sort of a special case where you have e to a number times x. Because when you have that, you go ahead and you simply copy. Maybe I'll do the steps. Copy the exponential function and then you divide by the number and the exponent. What's the number in the exponent? 2. So you divide by 2. Or you could say you put 2 in the bottom. Same thing. Exponential, natural exponential function, a number times x, you rewrite the whole exponential function, divide it by whatever the number is. Alright, so that's a little bit of a special rule too. And that's pretty much it for those rules. However, sometimes what about if you have coefficients? What about if you have the integral of 4x cubed dx? Coefficients for integrals, we treat them just like coefficients for derivatives. You just move them out front and they just tag along for the ride. Matter of fact, sometimes if you want to, you can actually move the number outside the integral, and now the problem really becomes, what's the integral of x cubed? Power rule, add 1 to your exponent, divide by the new exponent. So this 4 tags along, so it's still here, so those cancel out. So how about the integral of negative 1/2 e to the 3x? Negative 1/2 is a coefficient. You don't have to do this, but for now, just while we're learning, I'll just actually move it out just to make it very obvious. It has nothing to do with the integral. So now we have exponential function. We copy down the exponential function, divide by the number. So for this one, you'd end up with like negative e to the 3x over 6. So the coefficients just sort of tag along. Actually, let me do one more, just for a little practice. How about integral of 1 over 2x? Well, this 2 is like a coefficient. I can actually move it out front and say 1/2 times the integral of 1 over x dx. You might be tempted initially to convert this to the power, so I can do the power rule out of x minus 1, but remember, this is the exception. We can't use the power rule. In fact, at this point, we just go ahead and say the integral of 1 over x is the natural log of absolute value of x. So I think those are all the rules you're going to need to start doing integrals. So I'm going to look at the homework, 5.1. This whole first section simply says, find the indicated integral. It says, check your answers by differentiation. So they're saying in the book, you can always check your answers by taking the derivative of your answer. So we'll just do some of these. Hopefully you get the knack of it pretty quickly. Number 2, actually, I just did this a minute ago. What's the integral of dx? Well, what's really here? There's really a number here. What happens if you take the integral of a number? Whoops. You just add the variable Of course, we would just call this x plus c. And actually, I did this one too. Here they change the variables. What they do, a lot of times I use x, but you can use any variable. Integral of square root of t dt. Once again, let's put this in the form where we can use the power rule. Power rule says you add 1 to your exponent, divide by the new exponent. And don't forget the plus c. So by the time we simplify the complex fraction, there you go. How about number 6? Integral of 3 e to the x. Actually, most of these look like the examples I've already done because they're all pretty much the same. 3 is the constant. It's going to tag along. So we've got integral of e to the x dx. So 3, you copy down the exponential function. You divide by the number in the exponent, which is just 1. So really, 3 e to the x plus c. Now, something new. What happens when you have multiple terms and how about all right, added or subtracted terms in the integral? For example, everything we've done so far now, we've just had one term inside the integral. What happens if you have like 2 terms here? Well, in this case they're added, but the same rule would apply if they're subtracted. I'm going to write it out this time, but in the future you would never write this out because it just takes time. But the idea is you can actually just separate them into 2 different integrals, and you just integrate them one term at a time. So, not very difficult, very intuitive. If you were to guess what to do, that would maybe be your guess. So in other words, you would say, well, 2x squared dx to 2 tags along. Power rule says you add 1 and then divide by the new exponent. And integral of x dx, power rule, add 1, divide by the new exponent, and then at the very end, you would put your constant. So, now that we've covered that, let's do a few more. Like, how about, let's look at problem 10. Looks a little more complicated. 1 over x squared minus 1 over x cubed. Integral with respect to x. So I'm not going to write it out, but basically I'm going to do these one at a time. Actually, what I'm going to do, though, I'm going to convert these to make it very clear that I can use the power rule, right? So if I apply the power rule to this, you add 1 to your exponent, and you divide by the new exponent, and then the minus, and then add 1 to your exponent, and divide by the new exponent, and then you have your integration constant. So if I simplify this, this is actually negative 1 over x. This minus 2 and this minus cancel out. And that should be your answer. All right, let's do a couple more. Hopefully with practice, you'll get this done pretty well. All right, this one looks pretty messy. The square root of x cubed minus 1 over 2 square root of x plus the square root of 2. So I got three terms here, the integral of all that. What I'm going to first do, I think I can use the power rule for all this, but I need to rewrite it. Square root of x cubed is actually x to the 3 halves. Square root of x in the bottom, if I want to get to the top, that ends up being x to the negative 1/2. Now this is actually a number. So I'm actually not even going to change this to a, because it's just a number. I'll leave it for now. So I'm ready to integrate each one of these one piece at a time. So power rule says add 1. When you add 1 to 3 halves, you actually get 5 halves. And then the new exponent goes in the bottom. Minus the 1/2 sort of tags along. Now, the integral, you add 1 to negative 1/2. That's 1/2. Divide it by the new exponent. Now, square root of 2 is just a number. It's just a constant. What's the rule? When you integrate a number, you just multiply it by the variable. And don't forget this. Now this one, we probably should clean up a little bit. So this ends up 2 times x to the 5 halves over 5. This 1/2 and this 1/2 actually cancels out. Now you could convert these back to radicals, but it's okay to leave it like that. All right, a little messy, but not too bad. One more, 18. Here they decide to use the variable u, 2e to the u plus 6 over u plus natural log of 2. I'm going to take the integral of all that with respect to u. So here I have 2 times u. The 2 tags along. E to the u is just your basic, the integral of e to the u is just e to the u. All right. Because the number in front of it's 1, 1 goes in the bottom. This, the 6, here's that special rule when you have 1 over the variable. Remember, you can't use the power rule. But you have to use the rule that says it's the natural log of absolute value of u. Natural log of 2 is just a number. Natural log of 2 is a number. So this is like a constant. There you go. Looks a little messy, but when you just take them one piece at a time, not too bad. Well, let me do one more problem from a different section. I'm going to do problem 36 to show you how to do it, and let me read the instructions. So for this section in the homework, it says, find the slope at each point on a curve and use this information. All right, the instructions are actually very sort of confusing. So here's what. Let me just do a problem and explain to you so when you get ready to do yours, you'll know. What they give you is, it's like they give you a derivative. And then they give you a point on the original function. And for this one, the point is 0, -1. So it's like they're giving you a derivative. And what you're going to do is, you know, when you take the integral of a derivative, you end up with the original function. Because once again, like an integral reverses a derivative. So in this case, they've given me the derivative. They want to know what was the original function. And the reason why they gave me this point, we're going to see in a minute. Let me not even tell you now. Let's just start working out this problem, and you'll see why we need to have this point. So once again, let's make it clear. If you take the integral of a derivative, that equals the original function. So they're saying, here's the derivative, find the original function. So I'm going to take 3 minus 2x. This is going to be my original function. It's actually a pretty straightforward integral. Integral of 3 is just 3x minus 2. Integral of x, power rule says add 1 to your exponent, divide by 2. Then you got to be your plus c. So this is really f of x. So my original function is 3x, these 2's cancel, minus x squared plus c. But the problem is, I don't really want to leave that c in my original function. If there's a number there, I'd like to know the number. And that's why they give you this point. This point is like the x and the y of a point on your function. Now here I have f of x, but of course f of x can always be changed to y. And now if I plug that point in to this equation, I can actually calculate c. So I'll plug in -1 for y, plug in 0 for x. Turns out c is -1, so now I can finally say, the function is 3x minus x squared minus 1. All right, so those problems, they give you the derivative. They want you to find the original function. The way you find the original function is you take the integral of the original derivative, but then you're left with this constant, but then they give you a point on the original function that allows you to figure out what the constant is. All right, so welcome to integrals. Hopefully you won't find those too difficult once you get the hang of it.